Making P2nP is illegal, so if you do it at your own risk. Alright, this is John Black, super chemist, here to talk about the Henry reaction. The Henry reaction is a nitro-aldol reaction, same thing. You're making a beta nitro alcohol. If you know the aldol reaction, it's pretty much analogous to that. You get a nitroalkane, you get an aldehyde or a ketone, and you get some kind of base catalyst. And you mix them together and you come up with a beta nitro alcohol. Okay, so here's your nitro alkane and here's your ketone or aldehyde. I used a ketone. The R's just stand for any random hydrocarbon dangling off. They really don't matter what's dangling off. All that matters is the functional groups. Now you can see I have two positives here. Why are they positive? Because this one has an oxygen which is very electronegative. That means it wants to suck up on electron density. And if it does, it leaves this carbon with less electron density, making it partially positive. Now look over here, you not only have an oxygen, you have two oxygens and a nitrogen. All three things very electronegative. They're sucking electron density away from this carbon big time over there. Okay, and if you watch my nitromethane video, you'll know that a nitroalkane is actually an acid. Okay, it sucks up on electron density so much that if it loses a proton, right, a hydrogen, it doesn't matter about the negativity because these are so electronegative and there's so many of them that it just distributes that electron density so nice that it stabilizes what's left. So if you have two positives, how are they going to react with each other? That's where the base comes in, your primary amine. Okay, and you can have other types of bases. I'll get into that. Right now we're going to use the primary amine. It comes and it snags that hydrogen off of there. There's two hydrogens, even though they're not shown. Snags one of the hydrogens. When it does that, this is now negative because it took the proton, right? It took a positive proton and left it negative. Now you have a negative and a positive. Now they can link up like magnets, right? I want you to look over here. Here's your nitroalkane, right? And here is your ketone. Here's where the double bond used to be. You can see one of the double bonds fell over to connect these two molecules together. Right? You can see right there. And it left the negative charge. Remember, this is negative, so when you link both of these together, you're still going to have some negativity somewhere. That negativity jumps up onto the oxygen. And now, remember, this amine base is a catalyst. That means whatever it does a reverse thing later on so that it, like it gave up a hydrogen here, that means it gives a hydrogen here. So that it goes back to what it used to be and it can be reused again to take another hydrogen, right? When it does give a hydrogen, now you have this, okay? Now you can take that and you can extract it out of your pot and, purify it and you have this product. Then you can do two things with it, okay? You can either take your nitro group and reduce it, okay, to an amine, and it won't be able to reduce this because this is the lowest reduction that you can have with a hydroxy group. Or you can oxidize this, okay? You can oxidize it to a carbonyl group and make this into a ketone. Now, if you do that, you can only do it, see right on my example here, you can't do it because this is a tertiary alcohol and you cannot oxidize a tertiary alcohol. But if you started with an aldehyde instead of a ketone, one of these R groups is going to be a hydrogen. This one right here will be hydrogen. Then you can oxidize this up to a ketone. This won't be oxidized because it's already in its highest oxidation state already. But we're not doing that. We want to make this hydroxy group into a double bond right here. That's what we want to do. Now, so far, this reaction is pretty much spontaneous. You know what I mean? You can just mix all this stuff together and stir it for a while, and I think you'd have your product. And you can see, as soon as you add in the base, you can see color change. It'll start changing into a yellow and then an orange and then a red. But as soon as you put it in, it'll start turning yellow. You know you're making something at that point. No heat is required. No nothing. You just add it, stir it up. How do you get the double bond? And I'm sure the double bond forms at least a little bit, whether you heat it or not. But how do you get the double bond? You reflux. You heat it. Now here's what we just had up here, right? This right here we were talking about. Now let's say we want to get our double bond on there. I drew an H on here. You can see if I take the OH and I take the H and I pull them off, it makes H2O, right? Then, since one's negative and one's positive, you're pulling off a neutral thing, so what remains is neutral. Where does the double bond come from? It comes from this bond right here that holds the hydrogen on. The OH takes the electrons with it, right? It's negative, but the proton, the hydrogen, just comes off by itself. It doesn't take any of its electrons. So those electrons fall or swing, right, into this, make this double bond. The thing about this reaction is everything is reversible and everything forms an equilibrium. So when you make this, it actually goes back because it's reversible. It goes back to, back to the beta nitro alcohol. Okay, you make it and then it goes back, some of it at least, and it keeps making this until it forms an equilibrium. Basically, this and this is the same thing. I just like it drawn this way. Okay, I just flipped it around. These two R's are kind of moved down to here. That's it. But this is what you get. You get water, and you would get your product. But let's go into that equilibrium thing. Okay, let's do this first one. First, I'm going to switch it up to a benzaldehyde and nitroethane, right? So, and there's our primary amine. Here's what we would make. And if I flipped it, you can see the arrow. If I took that molecule and flipped it, it would look like this. Okay, these are the same thing. This is what we would make, all right? But if we heat it up and we start refluxing it, after we add the amine, we start refluxing it with heat. This is going to start dehydrating into our product, right? Or nitropropene. I'm making up numbers. I don't know what the ratio is, but let's say it's a 1-to-1 ratio for the equilibrium, okay? That means that this will keep making this until there is a 1-to-1 ratio between the water and this, okay? Let's do an example. Let's say we have 100 molecules of this. We heat it up, right, with our amine and our whatever. When half of this turns into the nitropropene, right, that we want, that means half of it is left. It didn't react, right? This part right here did not react. For every molecule of this that we make a molecule of water. So these have to be even. And we know there's a 1-to-1 ratio, so they'd have to be the same, right? We know that we have started with 100 molecules. If 50 of it got transformed, then we have 50 left over, right? Now, this is the way Kempler did it, and he used methylamine, and so he was kind of forced to do it this way. But let's say that you could take the water out. If you could take either one of these out of the pot, then you'll start producing more. The reaction will start taking off again. Why? Because you need a ratio of 1-to-1. Let's say I take the water, I could stick my hand into the pot and just pour out the 50 molecules of water. Now you have a ratio of 50 to 0. Until the ratio is 1-to-1, it'll keep making more. So let's say we do this. We do our 100 molecules, we make this. Now this doesn't react because it can't react anymore because you got a 1-to-1 ratio. We take the water out. Now you have 50 molecules left, right? We took the water out, so it starts making more of your product. But it also starts making more water, okay? So now you have 25. Now you made a 1-to-1 ratio. So it stops making your product again. But let's say you take more of that water out. Okay, now you got 25. And it starts making your product again and water. Now it's 12 to 12. My whole point is if you keep taking the water out, you'll keep making your product. Instead of ending up with a 50% yield, right? you can end up with a 50 plus 27 plus 25 plus 12, that's 50, 60, 70, 80, that's 87% right there. You do it again, you get 6, you're up into the 90% of a yield, you know what I mean? Because you took the water out, okay? And you let the equilibrium keep building up and building up. Now, keep in mind, and this is very important, so listen to what I'm saying, okay? Listen to this, this is very important. This is an analogy. This is not what really happens, okay? The equilibrium is actually between all 4 chemicals, the 2 reactants, and the 2 impurities that you make, the product and the water impurity. Those 4 things. It's a ratio between all 4. It's just too complicated for me to get into that right now. So I did this as an analogy so that you can see that the more water you take out, the more you can make of your product. Take the water out, you can make more of this product. Take the water, you know what I mean? It's not a 1-to-1 ratio between the 2 over here. It's a ratio between all 4 of them. So it's more complex. I don't want to get into it in this video. I just wanted you to understand that you can either get a 50% yield or you can get a high yield up into the high 80s or maybe 90s or mid 90s if you get the water out of the reaction pot as you make it. I mean, if you think about it, if it was a 1-to-1 ratio just between these 2 things, as soon as this molecule made 1 molecule of this, it would make 1 molecule of water and the reaction would stop. You know what I mean? But it's just an analogy. It's not an exact whatever. It's easier to understand when I say it that way, though. Just disregard that the 1-to-1 ratio would actually happen. As soon as you made 1 molecule of this, you'd make 1 molecule of that, and you'd have a 1-to-1 ratio. But this is an analogy. It's not exactly what happens. It's just to get my point across. Okay, I'm just going to read this part about the bases, okay? Because your catalyst has to be a base. Remember, it's taking off protons off the nitroalkane to get the reaction to go. And it probably takes off the hydrogen off of the beta nitroalcohol when it's trying to dehydrate it into your product, okay? It's probably the one who comes and grabs the hydrogen, although it could be the hydroxy group, you know, snags the hydrogen within its own atom, within its own molecule. That's beside the point. Let me just read this, because the only base I vouch for is a primary amine. It has to be a primary amine, as you got a definite fact it's going to work. But let me read this. One of the features of the Henry reaction that makes it synthetically attractive is that it utilizes only a catalytic amount of base to drive the reaction, so just a small amount. Additionally, a variety of bases can be used, including ionic bases such as alkaline metal hydroxides, meaning sodium hydroxide, potassium hydroxide, alkoxides, carbonates, and sources of fluoride anion. No one has fluorine. Or non-ionic organic amine bases, including TMG or DBU or DBN or PAP. It is important to note that the base and solvent used do not have a large influence on the overall outcome of the reaction. There are many factors, or not many, but there are a few, more than one factor, that determine stereoselectivity. I'm not going to go into the stereochemistry of this. If somebody really wants me to do a video about the stereochemistry, just let me know, but I think it's a little too advanced or whatever. So I'm not going to go into it right now. Now I'm going to go into 3 examples. The first example, we're going to talk about how to do this the way ChemPlayer did, with the no taking the water out. You just mix them together, reflux it for a certain amount of time, and when it's done, you have your product. The second example I'm going to go into is how to get this water out manually. How you can do it manually, get that water out, if you don't have a Dean Stark apparatus to do it. Third example will be how to get the water out using a Dean Stark apparatus. That way you don't manually have to take the water out. The Dean Stark apparatus just takes it out automatically during the reaction. You don't have to do anything.